Hey everybody, it's Mr. Sheeline here. This is going to be the video for the Unit 4.2 Power Notes. This video is only going to be concerned with the material in the notes. It's not going to be covering the check your understanding. So I'll have a separate video that walks through how to answer the check your understandings. And there's about 5 of them in this set of notes. And anyway, this is going to cover power, and we're going to see how power connects with energy, how it connects with work, and we're going to combine all these ideas together and solve some pretty easy, relatively easy, equations, and find some solutions as to how much energy, how much power, how much work was done or put into a system. And that's pretty much it. So let's just get straight to it. So before we get too far into, this little bit about power, we do have to kind of backtrack a little bit, and we've got to cover something that I think I might have incorrectly said we wouldn't cover last week. Those two things are potential and kinetic energy. So if I said that we were going to calculate this, I was mistaken. I completely forgot that we kind of do need not so much kinetic energy, but potential energy. But it's important to cover both of these ideas specifically because it's not because they're the same thing. It's because they are intertwined with one another for the most part, and so it's best to cover both. And realistically speaking, this should be review, whether it's from your freshman year or it was from middle school, whatever it was. We should have some sort of semblance of what kinetic energy is and what potential energy is. And before you even read this, when you hear kinetic, hopefully you have an idea of what that is, because we've been studying kinematics, okay? And kinematics is just the study of motion. So if you have something that's called kinetic energy, that must mean then, as it says now, kinetic energy is the energy of motion, okay? So, and then we'll get into potential here in a bit. Okay, so just to get to it. So like I said, kinetic energy, which I will denote either as K, capital E, or I will write down E sub K. So it just depends really how I'm feeling. I think most of the time I usually am in the habit of writing KE, then E sub K. So just keep in mind that's usually how I denote it. Okay, so when we do work on an object, energy is transferred into the system. Okay, so when the object gains energy, it begins to move, obviously. Or at least that's the idea, right? Because in order for you to show that energy was used and to show that work was done, you have to show that it has moved in some sort of direction in line with the amount of energy and the direction of the energy that's inputted. Okay, which makes sense. If you do work on a car by pushing it, as an example, it gains kinetic energy and begins to move. And we can calculate that by this. So here was E sub K is equal to 1/2 times the mass times velocity squared. Okay. Oh, and that that K is supposed to be subscript, obviously. Sorry about that. But similar to, not similar to, exactly like work and power, kinetic energy is scalar. So there isn't, but you can have negative energy and you can have positive energy just like work. And if you notice, if you derive those units real quick before I read that last line, if I can find my little stylus here. So if we were to derive the units real quick from this equation, what you'll see, and of course I don't have my little pencil here. Forgive me, let me pause this real quick. Come on. Let me pause this real quick, or hopefully it'll pop up once I get out of the slide. I'm getting quite fed up with the fact that Screencastify does this. Okay. I'll go back real quick. Okay. So if we derive these units, I'm going to use this color. So if we derive these units, so it'd be like 1/2 times the mass. So mass is going to be kilograms, remember, times, so this is mass. So that's mass, times velocity squared. So a velocity is going to be meters per second, but then it's squared. So both your seconds will be squared and also your meters will be squared. So where have we seen this before? Well, we've seen this like this before, Newton meters, and we've also seen it like this, joules. Okay, so this is part of that work energy theorem that's mentioned in the Dr. Dave, or Professor Dave, I should say, video. This is, again, what we call the work energy theorem. It's the idea that pretty much the work done and the energy that you're able to calculate are more or less equal to one another, or at least the change in energy is equal to the work done. Okay, so anyway, so what the point of showing you that is the fact that here we have for kinetic energy, we have and use the same units as we do for work. Okay, it's joules or Newton meters. Okay, let's go. Thank you. Okay, so that's kinetic energy. So remember, kinetic energy is the energy of motion, whereas in potential energy, which there are a number of different types of potential energy. There's gravitational potential energy that we have here. There's also what's called elastic potential energy. Now that we will kind of get into, I hopefully get into towards the closer to the end of the year when we get into elasticity and wave motion. So hopefully we'll get there, and that's where we'll be talking about springs. That's where we'll be talking about slinkies, that sort of thing. But for now, we're just going to focus in on gravitational potential energy. So what is gravitational potential energy? So for the most part, we denote this as PE or E sub P, or at least I do. And there will be you may run into other language where it's E sub G as well. But for the most part, these are the two that I typically use, most of the time being PE. So what is gravitational potential energy? Well, it is the amount of energy stored in an object due to its elevation above Earth's surface. Now, it's a funny thing, gravitational potential energy. It's not saying that there's some sort of immense amount of energy that's literally built up at the moment something changes height. It's not to say that as you move from one vertical position to another, that all of a sudden you're building up this energy, and at some point, under this idea that you would just explode or something because you're just this big old ball of energy. It's not to say that. What it's saying is that every time you move up vertically, you're increasing the potential for that energy to be transferred from your body at virtually, at not being used to being used in the form of kinetic energy. So looking at this little picture at the bottom here of this kid, it's to say something like this. It's to say that, if he's at this position right here, we'll say his potential energy is 0. Okay. But as he climbs, when he's at this position, okay, now obviously he's on a swing, so yes, he's moving. But let's just say he was stationary right there. So remember when you were a little kid and your dad or your mom liked to hold you up super high on a swing to spook you, okay, and they're holding you there. Let's say that's what's happening to this kid. So when he's being held there, his vertical, the vertical height, the vertical distance he is from 0 has increased. But it's not to say that somehow the energy is physically actually being stored. It's just to say once he's released, the potential energy this amount of potential energy should transform to this amount of kinetic energy at a certain point within his trajectory. And we'll kind of practice this a little bit. Realistically speaking, this material for potential energy is mainly just to get you to the equation, because we're going to use the equation to better understand power. Because we kind of need, and we also need kinetic energy as well in order to figure out how much power is used as well. Because what we'll see is that power has a very specific kind of unit, and we need to know how much energy is in a system in order to do that. And anyway, so that's why we're going into this and why we're kind of backtracking a little bit. But to kind of cap off with this, let's just kind of read through the rest of the notes. So the potential energy at a height of h above that point is equal to the work which was required to lift the object to that height, which, of course, makes sense. If the amount of kinetic energy it takes to go from say 0 to 10 meters, that'll be about, relatively speaking, should be about the same if you're going to go from the 10 meters to 0, is what it's basically saying. Okay. let's see. So like charging a battery, you put energy into a battery which can be used at a later time. Now, I don't really like this verbiage, but it's not a terribly bad way to describe it. The only problem I have with it is the fact that I explicitly talked about how it's not like you're building energy. As say you're climbing stairs, as you're moving vertically. It's not that you're accumulating energy. It's just that you're building up the potential for a higher amount of kinetic energy to be expelled. That we can say that's a potential to be expelled. But it works in the idea that it'd be like a phone battery, and the fact that, well, you're going to charge the battery, and charging the battery is like moving vertically, and the more you charge it, the idea being is that the more amount of energy that will be expelled once it reaches that point in which that energy can be converted from in the phone's case, in the form of chemical energy to electrical energy to like say light energy, sound energy, thermal energy, that sort of thing. Okay. And then anyway, yeah. Hopefully, again, just be careful with this, because again, don't want to misconstrue you here, or confuse you, not misconstrue, but confuse. Okay, so because gravity acts vertically, we use h rather than displacement for the magnitude of displacement, which, yeah, that's fine. I typically do that. Oh, excuse me. I typically do that, and we'll see that in the next slide here. Okay, so since energy is obtained at the top is equal to the work it took to get there. So again, this is that second bullet point. It's work is equal to the change in the potential energy, which is just equal to the mass times gravity times height. Okay, so here PE is equal to mass times acceleration due to gravity times height, mgh. And like I said earlier, we got to remember the potential energy equation and also the kinetic energy equation, because again, we need both of those in order to find the amount of power being done or used in a system. Okay. All right, so now let's get into power, and hopefully my little tool guy over here won't be too much. Okay, cool. Oh, now you want to work. Oh, interesting. Sorry. So power. What is power? So power is the rate of doing work or transforming energy. So this is a scalar quantity. Okay. So meaning it doesn't, we only really account for the magnitude. We do not account for direction. Okay. And the unit that we use for energy, obviously, that we should know already, is joule. Now, remember, though, power is the rate in which we use energy. So remember, rate is pretty much just how often do you use it. What is the frequency of the usage of the transformation of this energy? So because of that, it's going to be over time. And so what usually we put it over is seconds. So power is therefore measured in joules per second, and then joules per second is then basically or this is then called a watt. Is called a watt. So 1 joule per second is equal to 1 watt. Okay. Now at the bottom here, here we have the power equations. Now power is denoted by P, and that's something I probably should have put here at the top. So here, let me get my little handy dandy guy out again. So realistically speaking, power should be, it's denoted as P here. Okay. So it's denoted as P. So here at the bottom, we have P is equal to the change of energy over time. Or we could say P is equal to the work, the network, the net amount of work done over time. Okay, so that's to say that if we have a change in energy, it'd be however much that energy or how much that work changed over a certain span of time. And we'll practice that as we go along here. And I think I only have 1 or 2 more slides, and then we're getting into the check your understanding. So again, I'll have a separate video for that. So keep an eye out for that. I'll have that available to you soon. Okay, but let's just kind of finish this up here. Okay. So watts denoted as W. and also kilowatts. So both of these are watts we'll use quite a bit, but also kilowatts is quite a common. It's a very common set of units that we'll use, especially, and also megawatts. So you'll see an example here shortly about a particular energy plant in the UK that just pumps out a massive amount of energy. Okay. But anyway, so watts and kilowatts are commonly used to indicate the power of electrical appliances. So how much power they consume per second of operation. So here we have like a good span of how much energy, how much more power these appliances use over another. So here we start with a light bulb, and you can see the light bulb, relatively speaking, pretty low with just 11 watts. And then you have a razor here. The razor is 15 watts. The fan depends on the fan. Same thing with like the laptop and the computer that you'll see, depending on your model here, it could be using, somewhere between 10 to 50 watts, laptop 75 to 100 watts, for a security camera, 150 watts, et cetera, et cetera. So the idea is that, and remember, you've got to think about, well, what does that watt mean? Well, watt is how much energy is being used per second. So if you think about that, 210 watts is equal to 210 joules per second. So if you want to think about that, well, and I don't have, or actually, if you want to think about what that means, then what would not be a bad idea is to maybe kind of compare it to yourself. Look up how many calories. Look up how many joules are in calories. Find that conversion, and then just kind of have an idea of how much work you would have to put into a system in order for you to produce 210 joules every single second. And I can tell you it's a decent amount of work, especially if you want to watch hours and hours and hours of some sort of TV show in this case. Okay. But as you see in something that's indicative of this is that you can notice that as not only the watts get bigger, but also the appliances, for the most part, become larger. If they don't become larger, at least the use of the energy it becomes more concentrated, and it becomes a bit more obvious as to why it uses up so much energy. So in this case, here we go from a decent sized TV monitor and also a washing machine. We bump that up to all of a sudden an iron, and an iron uses up to, in this case, it uses up to like 1,000 watts. Not very big, an iron, and all of a sudden it bumps up to an oven. But again, it depends upon the object and specifically the work that it needs to be done. In this case, heating up things in order to press them. Okay, and hopefully you get the idea. Okay, so let's keep on trucking. Oh, and I didn't change the font on this one. Of course I didn't. And I didn't change the picture. Here, let me get that real quick. Okay. So, megawatts, and this is that watch me use it, the example I just mentioned a bit ago. So megawatts and gigawatts are often used to rate power of electrical generating stations. So what you have to remember, or at least know, is just, do you really need to know this for, say, a test? No, you don't. Just because that we never really went over it, and arguably you probably should have an idea, but mega. So mega is going to that's a denotion, and that's a prefixed range of SI units. So mega is denoted with a capital M, which I think we've done some examples of, and mega is equal to like 10 times, 10 to the, not 10 times. It'd be like 1 times 10 to the 6th power. Oh, come on. To the 6th power. Okay. Oh, my goodness. Here, let me get rid of it. Nope. I hit that. So it's going to be, so again, 1 times 10. Oh, my goodness. It's 1 times 10 to the 6th power. I'll just say it verbally, I guess. And then whereas giga is 1 to the 9th power, 1 times 10 to the 9th power. So these are pretty big. And just to kind of help you out here, think of it in this way. I mean, if you've done anything with computers before, and I mean like just look at file sizes. What you'll notice is that obviously a gig we should, and also just even through your phones and like phone storage. So imagine this, that just as a quick little thing on how far or how big the difference is between or kilo, mega, and giga are. So think of it this way: a lot of you have phones that will have storage of gigabytes. Usually somewhere probably they're at least above 100. Most phones, pretty much most phones nowadays. But if you don't, I mean, I just had an upgrade, so it's all good. But anyway, giga is, as we already know, is significantly larger than mega. And think of it in this way: way back in the day, old computers, there were floppy disks, and there were some floppy disks that could only hold up to 3 kilobytes. So, and kilobytes, if you've never noticed those will be usually like associated to how big like Word docs are, and a lot of times Word docs are like 15 to 2,000 kilobytes large, depending on how many words you're typing up in your file. So and then from kilo, it's mega, and that's an extra 3 decimal places, and then giga from mega is another 3 decimal places. So I guess this is a really long way of just saying giga and mega are huge. Giga is way bigger than mega. It's really all I'm saying. If I confuse you on what I'm talking about here, just look up the difference between them on Google. And it'll provide a much clearer, better example of what I'm trying to relay to you here. So anyway, mega and gigawatts are often used for power plants, which makes sense because power plants pump out a huge amount of energy. And not only that, just a huge amount of wattage, because it's having to pump it across a large amount of individuals all at the same time. Okay. So this rating indicates how much energy the station generates per second. So as an example here, we have the coal-fired Ratcliffe Power Station in the UK. It has been rated to hold a capacity, a capacity of 2 gigawatts or 2,000 megawatts, which is to say 2 gigajoules per second, or 2,000 megajoules per second, which is just insane. Okay. Oh, of course. Man, I've got the hiccups. I've got the yawning. Sorry. Horsepower. So, and then this will be the last slide before moving on to the check your understanding. So then, because we talk about power, we have to talk about horsepower. And there's going to be a reading this week that covers horsepower to kind of understand where exactly we get this idea of horsepower. Okay. So horsepower is still a unit of measurement of power. So what it is, it's 1 watt is equal to 0.00134 horsepower, or 1 kilowatt is equal to 1.34 horsepower. Okay, now it says look at the previous question. So this is referring to the very last, I forgot about that. It's referring to the last check your understanding. So if it doesn't make a whole lot of sense, this is why. But just looking at here, so let's just say that in check your understanding number 5, let's just say you happen to get the answer of 201.05 kilowatts. Okay, well, it's asking you now to convert that into horsepower here. So it would be 201.05 kilowatts times 1.34 HP, which is horsepower, which then equals 269 horsepower. Now, I won't give away all that much about horsepower, just again, because you'll have a reading assignment that covers it. So if you're wondering, well, what does horsepower have to do with anything? Just know that it's a unit that was pretty much put together before watts were put together. And it's a staple in more of automotive today than anything. Well, automotive and some other appliances like pressure washers also use how many horsepowers that it uses. So again, you'll have a reading assignment that will cover how much, why it is that it's still being used today, and also why it's called horsepower. Okay. So anyway, guys, again, yeah. So here's your check your understanding. So I'll have a separate video for that. So this is just covering these notes. If I confused you terribly and you need some help with this, make sure you hit me up during my office hours on Tuesdays and Thursdays. Also, remember that your final exam is going to be next week on Tuesday. Okay, so that's just a day more than a week from right now that I'm recording this, that you should be watching this video, which is Monday, December 7th. Okay, so remember, you got a final coming up. So prepare for that. If you have any questions about that, make sure you ask me during office hours. Oh my goodness, I'm so sorry. So too many yawns. And then if you still have any questions over anything, email me, text me on Remind, whatever you have to do. And that's pretty much it. So those are the notes. So if you guys still have questions, again, get a hold of me. If not, I'll see you guys in the next one.